Dr. Harminder Gehrawat. He did PhD from ISI, then postdocs in Israel and France, and now again in France with Flo. And he will be speaking about rumbles and cops and robbers and treatments. Okay, over to you.
Thank you. So today we will be looking at the fundamental question: when does a graph has large treewidth?
Please give me a mic. You have a color?
Mic is there.
Okay, good. France, now again in France. You have to switch on. It's switched on.
working. Is you take?
Hello.
Over to you. थोड़ा ऊपर कॉलर में लगा.
Hello. Is it working now?
No.
When does a graph has large treewidth? No, it's green light is green. Okay. There is green light, but it's not working. Hello.
थोड़ा ऊपर लगा. कॉलर में लगा.
Hello. Is it working now?
No.
Yeah.
In the streaming, it's
Green light is green. There is green light.
if it is working in the streaming, it's okay because it's clearly audible.
Hello.
Okay. Then
Hello.
please start.
Hello.
Hello. It is audible. Harminder, it is working for the
video is done?
Yes. So that is more important.
Then we can drop this.
No, you please use this working in the streaming.
It's working for the video.
Yes, sorry.
Okay. Let's start. Hello.
Please start.
Hello. I just thought it's not too loud for the video.
It's working.
I'll try to do it.
Please start, you know.
Then we can drop this.
No, you please use this.
It's working. What I think is, because if it's audible to them, it will be too loud for them. Use it here. I just thought it's not too loud for the videos. I'll try to do it.
Please start, you know.
Because if it's audible to them, it will be too loud for them. Okay, let's start. So today, in this session, we will be talking about when does a graph has large treewidth. So let's say we have a graph. We are asked the question, what is the treewidth of this graph? Till now, the techniques that we have learned are equipped to tell us that the treewidth of this graph is at most this much, because we can give a witness, which is a free composition. So we can say that, okay, this particular graph has treewidth at most large. But how do we say that this is an optimal treewidth, tree decomposition? For this, we need to have some notion of a lower bound. And for this purpose, we will be looking in today's lecture at some new tools and techniques that were developed in 80s. And we will be looking how to use those tools to give good lower bounds. So, again, I will say that the main question today is, when does a graph has large treewidth? And we'll start with some definitions. Let's say we have a graph G, and two subsets X and Y of vertices of G. We say that X and Y touch if either they intersect, these two, they have some intersection, or there exists some edge between two vertices, some vertex X from X and Y from Y. So if this happens, we say that these two sets touch. So remember this definition. Next, we have a notion of brambles. So brambles, the term comes from the rose vines. The way the rose vines are intermingled among themselves. Similarly, we have a mathematical notion in graphs, which is called bramble, which is a collection of subsets of BG. So a bramble is a collection of subsets of BG which are pairwise touching each other. So, yeah, is the definition clear? We have some subsets of our vertexes which are touching each other pairwise. So, let's say that I have a bramble B. It will be a collection of subsets, let's say touching these. Touch means two subsets touch each other if either they intersect or they have an edge with one endpoint in each of these two components. Okay. So a Bremble is a piece of connected components, is a collection of connected components which pairwise touch each other. And okay, so this is a Bremble. And next thing is we have a cover of a Bremble. This is very intuitive. A cover is a subset of vertices of my graph such that it has a known empty intersection with each of these components of my Bremble. And next thing is cover.
Can you write the definition?
The definition? X is a cover of D if for each I in J Ci intersection with X is not equal to empty set. Yes. So cover is a hitting set of my Brembles. And
So again, what was the connected and touching, right?
sorry,
What was the definition of a Bremble? They must all be connected and they must all be touching.
they must touch each other. Okay. So
X also touches all the subsets.
touch. Bremble is a collection such that Ci is connected for I in K and Ci intersection and Ci and Cj touch. This is very important, touching, and the definition of touch is here, either they should intersect or they must have an edge across each other. Neighborhood of this whole set should intersect here.
So, just two questions. Like, is touching the general term used for this? Because usually we use overlapping for this. Touching is just for the boundary.
Because it's not just overlapping, what might happen is that there is some vertex x in Ci and y in Cj and xj is an edge x, y is an edge in my graph. Still I call them touching.
Breathe.
If S is belong in Ci and S is belongs in Cj also, that also okay or not?
Yes, then they overlap.
Yes.
And then also they are called to be touching.
So basically, the closed neighborhood must intersect.
Intersect with each other.
And each Ci is representing the vertices.
These are connected components of my graph. C1 through Ck are connected components and Ci and Cj must touch.
You mean connected sets,
Connected subgraphs may be
not connected components.
Connected sets, yes. Sorry. These are connected sets, connected subgraphs.
CIs are disjoint or
No, they don't need to be disjoint because here you can see, by definition, they may touch each other. So, again, to begin with, two subsets touch each other when they have either a non-empty intersection or they have an edge which goes across them. And Bremble is a set of connected subsets of connected subgraphs, and with two extra conditions. One is that my CIs must be connected, and the other thing is that they must touch each other. And So think of them like vines of a rose that are going, and they must be either overlapping or they must be very close to each other. And cover of my bramble is a set of vertices that hit all the these connected parts. These my brambles and these are my components of my bramble. Is it clear or should I say once more? Because this may be very important. After this, there is no coming back.
Will you give an example?
Instead of CI, I think you should write G of CI, right? Connected means there is new subgraph.
Yeah, so right now I was calling them to be subgraphs,
Okay.
but you can do that as well. So I'll be abusing this notation a little bit for the ease of presentation, where this CI will also be considered a set and also G of CI. Okay, I'll give an easy example. I was kind of saving it for later, but let me do it right away. For example, this is a graph, and if you want to, if I want to make a bramble set for this graph, one part can be this, and other part can be this. So these two components, they are connected. This is connected in itself, this is connected in itself, and they touch each other. And this is also this is a bramble. Now the voice is back. So this is also a bramble because this component, so let's call it C1, call it C2, and this is C3. So C1 and C2, they touch each other because of this touch, and C2 and C3 touch each other because of this edge. Sorry. Yeah, thank you.
Not necessary.
No, they need to touch each other. It was wrong before.
No.
No, they are touching here.
Now you can take only one vertex also. After this.
No, I increased C3.
Then if you do not increase, it is not bramble.
This is not bramble because C1 and C3 were not touching each other.
C1 and C3.
They should touch each other. Everybody should touch everybody. It's like a family.
But C2 and C3 are touched.
Yes, they must touch. So C2 and C3 are touching now. C1 and C3 are touching here. And C1 and C2 are touching here. So everybody is touching everybody right now. So also, bramble should not be exhaustive in the graph, in the sense there may be some vertices which are not part of my bramble. This is not a necessity. Bramble is just a collection of subsets of my graph such that they touch each other and they are connected.
So do you mean C1 is touching with all of C2, C3, Ck?
Yes,
Like this?
yes.
But you can always extend a bramble to make sure that all the vertices are covered.
Yes, you can take the whole graph and it's a bramble.
And also add the left vertex to the set. So adding a vertex would not violate property.
Adding a vertex will not violate a property, no.
Can it just
It may violate a property, you have to add it nicely. Yes. Now you cannot add this vertex to my
I
bramble.
mean, yes.
You have to take everything, but then you can take the whole graph also as a set and then it's a bramble. But you can always extend to contain the whole graph.
So a key, if you take a key and all the singletons, it will be a bramble.
Then it's a bramble, yes.
Can it just be like one element, like just one C1 in it?
Yes. And it will be clear later that we want more things. Yeah, it can be just one element. In fact, it can be an empty. This is also a bramble by definition. An empty set is also a bramble. Okay, cool.
So now you
showed a bramble, right?
Yes.
The cover for this.
Yes. Now the cover for this bramble is a hitting set of this bramble. For this particular one, let's see, this vertex and this vertex is a cover.
Which one?
It hits C1 and C2, and this hits C3. You can take any other vertex from C3 as well, but these two hit all three brambles. All components.
Suppose that the corner vertex was not there in C3.
Okay.
Still, it is like it's a bramble.
It's a bramble,
But
yes.
now, like you have to choose.
Now you can take this vertex.
C3 is not included in bramble.
It's simple hitting set of this bramble.
That's why not.
So let's take another example. Let's have it complete graph. It's a discrete format. So this is my complete graph, and let's say I want a bramble of this graph. One bramble can be, I take all the vertex set. It is a bramble. But if I take any subset of this graph, it is still a bramble. For example, if I take these vertices, it's a bramble. But the cover of this bramble is all of my vertex set. Alternatively, what we can do is that this is also a bramble because these two touch. Now my cover of this bramble are two vertices. I can take any two vertices and it's a cover. One bramble can be, this whole graph is a bramble, and any vertex is my cover because it hits my bramble. So, and finally my empty set is also a bramble here.
So, in every general graph, every vertices can be a bramble.
No.
In
Sorry,
graph.
in planar graph?
No, every graph. Whatever.
No. It has to satisfy the proper CICJ.
This is not a bramble because my bramble C1 and C3 don't touch each other. For complete graph it's true because everybody touch everybody. Here C1 and C3 do not touch, and similarly C4 and C2 do not touch. But now I guess it's a bramble.
No.
Yeah, sorry. You have to, yes. I have to make it complete.
Is
Yeah.
this a characterization that one vertex set is a bramble if and only if the graph is complete?
Let's see. We'll come to it. Yeah. I was saving these examples for later. It's much better to give them in the beginning. It's my first lecture, you see. So, okay, these are brambles. Is everybody clear with the definition of a bramble?
Yes.
Great, thanks. Now, another definition is order of a bramble. This is minimum size of a curve of B. Observe that whenever I say order or anything, this is a property of a fixed bramble. This is not a property of the graph. This is property of a bramble B. So order of a bramble B is the minimum size of a cover of B. So again, for example,
But non-trivial, right? Otherwise you can take empty set. Okay.
it can
This is the
bramble
You are
B
given
is fixed.
a bramble. Okay.
Yes, that's fine.
Got it.
Upper bounded by k.
Of
Upper bound is k.
for what?
Order.
What is K?
K is the size of
Number of connected components in the band.
Yes. Upper bound is k. Yes.
And if all the subsets are touching in the second way,
Yes.
then it is exactly k. In the second way. Okay.
Yes. 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 Yes.
What will be the size? Size means number of elements.
Number of elements in the cover. So let's say X is a cover of B, size of X is equal to this. So minimum number of elements in X. So minimum size of a cover of B is called order of my Dremel. Is everybody up to the order? Yes. Yes. X is a subset of my vertices of my graph, original graph G. Okay, I am going to remove the definition of Dremel for now. Okay, now the theorem that we will be looking at today is treewidth of my graph G is less than k if and only if there is no Dremel in G of order greater than k. So this is the main theorem which says that my graph has low treewidth, which means my graph has treewidth less than k, if and only if there is no Dremel in G of order greater than k, which says if my graph has a Dremel of higher size, then my treewidth cannot be smaller. This is the main theorem that we want to prove, and if you observe, this is a min-max kind of thing. I am trying to here reduce my treewidth, and Dremel is, if I want to show that there exists a Dremel, I can always show that there exists a Dremel of zero size, of order 0. What we want is that we want a Dremel of as much order as possible to give a lower bound. And this is the thing that we want to prove today.
And both are strict, so there is a gap of 1.
There is a gap of 1 because in the treewidth, yeah, thank you. Thank you for this note, yeah. There is a gap of 1 because in the treewidth definition, the definition of treewidth is the size of maximum bag minus 1. Here in our Dremel, we'll have very nicely, it will match, the order of Dremel will match the size of the largest bag of my graph. The size, maximum order of a Dremel. Okay. So, if you see, this says that treewidth less than k is no. So first we will prove the following result, that my treewidth, first part, this has two components. We will prove the forward direction first, which is relatively easier, which says that if my treewidth is less than k, then there is no Dremel of order greater than k. No B of order greater than k. And to this end, we will present a proof, and so let's say that we have a 3D decomposition, 3D of my graph G. And what we will like to prove, that there exists and B is any Dremel. What we will prove, that there will exist one bag in T that will contain all of this Bramble. That will cover all of this Bramble. That will be a hitting set of all of this Bramble. And hence, it has order at most K. Okay. So, how do we prove this? We'll prove this using contradiction. Suppose not. So, how do we begin? Let's say that we have two bags.
The TVs are optimal tree decomposition or planarity?
For any tree decomposition, I am giving this claim. I am making this claim. So, let's say I have T1 and T2, which are adjacent vertices in my decomposition. Now, look at the intersection of T1 and T2.
So we should start with a tree decomposition which attains the minimum.
No. Any tree decomposition, what I am trying to say, that you take any tree decomposition of my graph G, there will be one bag of my this tree decomposition that will hit any Bramble of my graph.
Any
Of my graph. You give me any Bramble of my graph, there will be any tree decomposition, there will be some bag of my tree decomposition which will hit all vertices of this Bramble, which will hit all the sets of my Bramble, all components of my Bramble. Okay. The proof is very, very simple, in fact.
T1, T2 are bags or?
Of my tree decomposition.
T1, T2
Are bags of my tree decomposition.
Bags or no?
I abuse this notation as well. Whenever I say bag, it means it means both things. When I say T1, it means it contains all the vertices that are inside the node T1. You can write this as well. T1 and T2 are nodes of my tree decomposition. And T1 has a bag. There is a bag that corresponds to T1 and there is a bag that corresponds to T2. Look at the intersection of that bag. So V of T1 intersection V of T2.
So
Look at this
basically
intersection.
You view your tree nodes as collection of vertices and take the intersection graph.
Yes. But now I'll take advice of Rohan and I'll refer to them as nodes.
Okay.
And my V of T1 will represent my bag and V of T2 will represent the bag. And look at the intersection of this bag.
T1 and T2 are any bags?
Any random bags of my graph. Or any random nodes of my tree decomposition.
But then the B is a Bramble. How will you use the direct components?
I will. Allow me.
Is there age between T1 and T2?
Yes, these are adjacent nodes of my tree decomposition. So T1 and T2 are adjacent nodes of my tree decomposition. This is an edge in my tree decomposition, and what I will do in the end, I will like to orient this edge. But first, look at this particular intersection of these two bags. Now, if this is either this is a hitting set of my Bramble. If this is a hitting set, we are done because both of these bags are a hitting set of my Bramble. So let's assume that V of T1 intersection V of T2 is not a hitting set. It implies there is some component C in my Bramble B which is not hit by this intersection. Cover.
So you have a collection of sets of vertices. Like you have this C1, C2, C2. Hitting set is if that set intersects with each of them, non-empty intersection. So it is like hitting each of them.
It's a cover.
It's covered. Also. Hitting set is more general.
Yeah, here. Okay. So, yes. So, is it clear now? What is the hitting? What is the cover? So, let's say if this is my cover, a statement is done. Because both of these bags cover my whole Bramble. But if they do not cover, there exists at least one component C in my Bramble which is not hit by this particular cover. So there exists some component C which has such that C intersection with this component is phi. V of P1 intersection V of P2 is equal to NP set. Okay.
So why are you considering the intersection as a power?
I am saying because intersection is a set of vertices. Either this is a cover or this is not a cover. If this is a cover, I am happy. We are done. If this is not a cover, I am saying there exists some particular component in my triangle which is not hit by it. It implies that this component C intersection with this is phi. But as we have discussed yesterday, as we saw in the tutorial also, that this is a separator in my graph. So C either lies in this direction or C lies in this direction. But since everything in my triangle, is it okay? C either lies here or C either lies here. But since everything in my triangle touches each other, all of my triangle either lies here or lies here. Because it is not possible that they touch and come here without going through here. Okay. So either all of my triangle lies here or all of my triangle lies here. So if my triangle lies downwards, I orient this arc like this, else I orient my arc like this. If it lies upwards, I orient my arc upwards. If my triangle lies downwards, I orient my arc downwards. So if this was my tree decomposition,
this can be a possibility that that C is touching VT1 but not the intersection part.
yes, that is a possibility.
So some of the subgraphs in the bramble can pass through this intersection, right? May not be all of them. Some of them can lie both sides, right? They can pass.
No, they cannot lie both sides.
So those which are touched by
their common intersection should be somewhere in above or below, but there could be some subgraphs in the bramble that can pass through the intersection, right?
There can be some subgraphs that can pass through the bramble. Yes, but they cannot be present here as well as here. Because this is a separator. You remove this, the graph becomes disconnected. If there is something that is passing through here, then this is still a connected component. It is not a separator anymore.
No, he is saying that there will be some component that passes through this entire medium separator thing.
Yes.
And like, isn't C, some elements are in the above, some elements are below, and some are in the intersection.
Yes, but then C cannot be completely on one side.
Yeah.
Yes.
So I think what is
see some other component.
So for example, if your bramble contains the subgraph C1, C2 and C3,
yes,
right? And it would be that the common intersection is somewhere above at a common vertex, for example.
So you are saying this is my C1.
Yes. So C2.
This is my C2.
Yes.
And this
similarly,
is
C3 can go from above.
this is my C3. But how now C3 and C1 will
So
touch?
C3 can also follow the similar path as C1 and can go to the intersection of C1.
Okay. You are saying, I just need it once more. This is my C1. This is my C2. This is my C2. And this is what you are saying, right?
Yes. So it is possible, right?
Just give me 1 moment. This is C1 touch here, C2 touch here, C3. and they touch somewhere here. And if I move this, C1 is completely here. Yeah, but okay. But C1, okay, maybe I said something in a misleading manner, but C2 and C3 are here also.
Yeah.
All of my bramble still lies on one direction, one side. This is what I wanted to say. All of my bramble lies towards C1 since it's a connected, since it touches each other. So I orient my arc towards the direction where all of my bramble lies. So I orient my arc towards the direction where my bramble lies. And at each point I can do this.
So where C lies, right? The C you discovered with intersection.
That the C where it does not touch.
Right.
This part does not touch, does not cover does not hit at least one of something which is C1 here. I orient towards this part. Yes, but since C1 is there, C2 and C2 must also travel there because everybody touches there.
How do you say that the vertices of this in between set is also in the upper part?
I'm not saying there is at least one vertex of C3 that is above because it has to touch C1. And yeah, it has to be here.
So then you are like taking C3 minus this part.
I'm not taking anything. I'm just saying that there exists some C1 that is not hit by this intersection. That is above. Since it is above, this intersection do not touch here, and everybody touches here. There should be at least one vertex of all of my bramble that reaches here.
So there is one more problem because of the definition of the touching, if we consider the second definition, where two verses are sets are distant, but they touch with respect to the
Yes, so it has to be here still.
So maybe C2 and C3 are ending up in the intersection part, and they touch C1 with respect to edge.
Yes.
That lies above.
This is what will happen in the end. This is what will happen in the leaf. And this is where we want to reach.
No, this cannot happen because
they are going
this cannot happen
above.
This property that is separate.
Not here. It will happen in the end.
And then we can say that this is
We will keep marking. What are you saying? You can please repeat yourself.
So I am saying that if you consider the second property of the touching,
Yes.
where two sets could be different with respect to
Yes, yes.
they are touching with respect to edge.
Yes.
It may be that if you are claiming that C2 and C3 both should go above this intersection,
Yes.
but it might not be true.
Let's say C1 is not here. No vertex of C1 lies here.
C1 could lie here, but C2, C3 may not lie above because they are in the intersection part.
Let's say some vertex of C1 lies, like the no vertex of C1 lies here. Let's say that no vertex of C1 lies here.
Like no vertex of C2 lies above the intersection. He's saying that.
Yes. So C2, C3 can lie in the intersection.
Yes.
But C1 lies just above the intersection in the same line. In the same line. C1 could be here.
C1 could be here. Then everything lies. Then still I orient in this manner.
Okay.
This is what I'm saying. There is no problem till here. I will keep orienting till now. But in every edge, I can still orient. The whole idea is I can orient every edge. Okay? Since I can orient every edge and we have a tree, at least one vertex will be a sink. And what will that vertex be? That vertex will cover at least one vertex from every bramble, by definition.
So is there a possibility that C1 lies in more than one bag?
C1 lies in a lot of bags, yes. All of these, even one vertex can lie in many bags, and C1 is a group of vertices, so it can lie in many bags. Many.
So how will we orient those edges?
Because at least, again, I look at this intersection, C1 lies on one, since it does not hit, and it's a separator, at least one of my components lie either towards up or towards down. I orient towards where my people are living. So, let's say this is my set. This does not hit, my set does not hit C1. Because it's a separator, either my C1 lies here or my C1 lies here. Is it okay? And by here, it could be here, 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 everywhere, but it's not here, not in the intersection. If it's not in the intersection, it is exclusively in towards one of these two. So in my tree, this is my node T1, this is my node T2, this is my T1, this is my T2, this is my intersection, this is my intersection. And now I am blind. What happens here? I don't care. I consider everything here one thing and everything above one thing. If the person that is not hit C1 lies here, I orient this manner, otherwise I orient towards down. This is what I do. And since everybody touches C1, everybody needs to reach here. And it will keep happening. Even if you want to touch C1, you cannot touch from here. You need to be present at least here.
Because of the second property of decomposition that is there in a graph.
Yes, that is also there, but it is also a property of the Bramble. Because the brambles touch, and since I have a bramble that lies completely above, I have a bramble C1 that lies completely above, nobody from here can touch because this is a separator. It has to be present here. So all of my bramble lies on one direction. I keep moving in that direction. In the end, I will end up with either a leaf or I will end up with a sink. It might happen that not necessarily my sink is a leaf. In the end, I end up at a sink, and that sink will be a hitting set or a cover of my bramble.
There will be a unique sink, right?
No. You can read sink very.
At least one sink.
No, there will be same bag, right?
There can be same bag many places, yes.
But at least one sink should be there.
Wait.
Oh, I mean, either you will find an intersection.
Yes.
Covers at some point before reaching to a sink, or you will reach to a sink.
Or you will reach to a sink.
If you find an intersection, then you are happy.
Then yes, we stop immediately.
No,
Yes.
otherwise you will reach a sink.
Yeah.
So after we get this sink, how will that ensure that it will solve the components?
So we are going at every step. And there is point collection.
So let's say at this place I am oriented this downwards. The reason I oriented is because I am saying everybody lies, all of there is a bramble that lies completely in this direction, and since everybody touches it, everybody is here. Let's say I am also coming from this direction, and here also I say that at least one bramble lies, at least one component lies towards here, and since everybody intersects, they might be coming from anywhere, somehow they reach here as well. And it can happen from all directions. Either I find a bramble, either I find a cover immediately, otherwise if I don't find a cover, I reach to a sink. If you start orienting the arcs of it, the edges of a tree, you will end up with a sink. And what are all these people telling to the sink? Every neighbor of the sink is telling to sink that there is someone that you are hiding, that is not accessible to me. But everybody, since everybody needs to touch you, everybody else that is accessible to me is accessible to you as well. So somehow everybody is reaching to this sink. All of these bramble components are reaching to this sink, and this is the proof.
Then that band is a cover and the size of the band is
Treewidth, and hence you take any bramble of your graph, the cover of that bramble, the order of that bramble my bramble B is less than equal to treewidth plus 1. This is my first result, first direction. And this is a proof of this statement, that treewidth of G, if it's less than K, then every component, then there cannot exist a bramble of order greater than K. Because if your treewidth is less than K, then any bramble you give me, there will be a cover of this bramble of size at most K. So there cannot be any bramble of order greater than K.
Okay, just to understand the semantics of it, when you say bramble, are you talking about all the sets or do you call them by a different name? Because somehow I'm getting confused.
Bramble is a collection.
It's a collection. So the individual set itself is also a bramble?
It's a component of my bramble.
I think you are using it interchangeably sometimes.
Okay.
When you say all the brambles are above the separator or below the separator,
Okay.
you actually mean each of the components are.
Each component of this bramble, yes. Okay. So now, since we have this, let's try to prove something which you have proved yesterday. Yesterday we all proved that, let's say we have a K by K grid, and we said that treewidth of my K by K grid treewidth of this graph is less than or equal to K. Today we want to show that treewidth of this graph, grid graph, is equal to K. And for this we need to show that my treewidth of G is greater than or equal to K. And can you now try to see why the treewidth of this graph should be greater than or equal to K? In this direction, we need to show that there exists a bramble of order K. So, can anybody point out a problem?
Yes. 1 and 3 are not available.
Yes. So 1 and 3, they are not brambles because they don't touch each other.
So one horizontal.
Yeah, sorry?
They touch each other.
No, 1 and 3 don't touch each other.
1 and 3, 2 and 4.
1 and 4.
So I can start like one line and this one. First row and first column together, and second row and first like that. First row and second column, first row and second. This one and first column. And
Sorry.
Then
Yeah.
first
row,
column and second. Yeah.
First column and second row.
Alright. And first column and third row like that together. First column and fourth row.
Yes. Yes.
So altogether 3 of them I got.
Yes. What is the order?
K.
No, you take any element from here.
K plus 1.
You take any element. Order is 1.
Order is 1. Because always in every
This is your
K plus 1 size.
So I can take first column, first row, second column, second row, third column, third row, fourth row.
Yes, let's try that as well. So you said something like this, right? This, and then second row and second column in one row. Okay.
Same we can go there, just center changes diagonally.
Just center changes diagonally.
Yeah, I mean, intersection point change diagonally and this 2, 2, 3, 0.
Yes?
He was just trying to show whether my example is correct now. He has an answer with him.
I have the answer.
But he's just
Yes, of course. Yes. So, maybe this is correct. I'm not sure. But let's come to that. I'll give you one example and a proof. So what you do, you take a bit more components than what you suggested. You take for every I and every j, you take C, I, j. Like this column, row I, column j. So you take column 1, row 1, column 1, row 2, column 1, row 3, all of them. Then you do the same for column 2. So you take column 2, row 1, column 2, row 2, and all of them. You take k square components, and now it is not very difficult to see that if you don't take k vertices, then by pigeonhole principle, you will miss at least one row and one column, and since this was also your component, you will miss this component. So if I take my Bremble as this set, my Bremble is equal to row I, column j for all I, j in A. If I take this Bremble, if I take any set X which contains less than k vertices, then I will miss at least one row completely and at least one row and one column completely by pigeonhole principle. And since this was my component, it cannot be hit by anything else. So grids have treewidth exactly equal to k, because we yesterday found a 3-degree position of width at most k. And in the beginning,
we can also say that if we take the ith vertices, then it hits everything. Right? Oh, but it's not covered for every Bremble.
It's covered for every Bremble. Also, if you take every row or every column, it's also a cover for every Bremble.
No, I was giving a k.
Yes, a k Bremble. If you take all the vertices of a row, it hits everybody. Yes. Or every column. If you take one vertex from every row, one vertex from every column, it will. If you take one vertex from every row, you'll hit everyone.
Yes. Here you have k square components, right?
Yes.
What is the minimum number of components with which you can do the proof?
I do not know. I should have, yeah. Interesting. I don't know actually. Okay. So this, and also we saw in the beginning that if we have a complete graph on n vertices, we can have a Bremble of order n by putting every. So I have kn, my Bremble is equal to every vertex v in v of g. And in this case, the order of my Bremble is n. And wait, yeah, order of my Bremble is n here. Am I making a mistake?
Yes, you have to give a second bracket again. This is a set of sets.
Yes. Okay. So, is it clear why some graphs have large treewidth? Do you get the motivation to study Brembles? So, we have seen that trees in fact have large treewidth. Sorry, not trees, grids in fact have large treewidth, but Robertson and Seymour in 96 proved in fact something very strong. Now, did we talk about minors yet?
Not yet, but you can just say what is contraction and say.
So I will speak, I'll say something about, I'll just give the definition of minors and so we say that H is a minor of G, or G contains H as a minor if we can reach H from G via these three operations in any order. One operation is edge deletion. We can delete edges from our graph G. We can delete vertices. Of course, when we delete a vertex, we delete all the edges incident on it. And the third operation is edge contraction. What is edge contraction? Let's say that UV is an edge. Then we contract UV inside the graph to make a new vertex. Let's call that vertex W. And neighborhood of W is equal to neighborhood of U union neighborhood of V. So let's say it was connected to these three vertices. This was connected to these two vertices. Then I make a new vertex W, which is connected to V1, V2, V3, V4, and V5, all five vertices. I connect this new vertex to all five vertices. So I guess we will be talking about this in better details. But this is a basic definition of a graph G containing H as a minor, or H being a minor of G. This is very important operation. In fact, from the place where treewidth and most of these results are coming, this was the graph minus project. Sorry? Yes, you contract to a simple graph. Now, the interesting thing is that if a graph G contains H as a minor, then treewidth of G is greater than equal to treewidth of H. This is what I needed. So, if your graph contains H as a minor, then treewidth of your graph is at least the treewidth of the minor. So, in these terms, we say that treewidth is closed under minor relation. Okay, and this will be proved, I guess, later in this course. This is this. Then Robertson and Seymour in 1996 proved a very strong result, in fact, that not only grids have large treewidth, but in fact they are canonical in some sense. And how they are canonical? They proved that every graph G with treewidth greater than or equal to f of k contains a k by k grid as a minor. This is a very strong result. Proof is beyond the scope of this course. It says that if a graph has high treewidth, somewhere a grid is hiding in the graph. If your graph has high treewidth, somehow, somewhere a grid is hiding in the graph. Yes. So the minimum value of this function f has been improved. This f of k has been improved 3 times. Initially, it was proved without a. Did I make a mistake again? Sorry, it was 86. Initially, it was proved to be 2 to the power k to the power 5 by R.S. in Robertson, Seymour, and Thomas in 1904. They proved that if my graph has treewidth 2 to the power k to the power 5, then there is a k by k grid hiding somewhere. And it was a very long-standing open question whether this bound can be improved to be polynomial. And it was proved to be k to the power 98 by Chekuri and Chujoy in 2016. And very recently, this has been improved significantly to k to the power 9 by Chujoy and 10 in 19. So right now, if you have any graph which has treewidth more than k to the power 9, somewhere there is a grid hiding of size k by k. C is Chekuri, Chandra Chekuri, and Chujoy, Julia Chujoy, and this is Chujoy, and T is for 10.
T is not Thomas.
No, this is Thomas.
So is there any conjecture? What is the?
It's polynomial, I do not know if there is a conjecture. But this paper requires a very big machinery to prove this bound.
What machine?
40 pages. Beyond the scope of this course. And beyond my understanding.
So no theoretical proof is there.
Sorry? It's theoretically proved very nicely. It's a very nice result.
There is also no known lower bound?
No lower bound. K is trivial.
Of course,
Yes, square, right? If you take a complete graph,
Yes.
you will find the root of k square,
Yes.
square root k, right? I mean, kn means square root n times square root n. So that's called k squared.
So this theorem, the characterization using the other directions.
Sorry, I missed your question. Can you please repeat again?
The other direction of the theorem.
I will prove.
Sorry.
Yes, I will prove.
So can you again just one before going there for the variable RICJ? How did you prove that at least k?
At least k, because
General principle.
yeah, if you take less than k vertices of your grid, for sure you will miss one row and one column. So let's say that you miss ith row and jth column, and there is a component in your bramble which is RICJ. You cannot hit this component.
So cover of size k means those k points and
The k point sign. There you need at least k vertices to hit every component of this bramble.
so if I have a cover k means I need k different. So what do you mean by the cover k of this bramble?
I am saying that this bramble requires at least k vertices to hit all the components. And you want to maximize, because this is a lower bound, you want to come up with a bramble that requires as many vertices to hit as possible. You require your hitting set of your bramble to be as large as possible, to give a lower bound on your treewidth.
You are proving that was greater than equal to k, right?
Huh?
There you are proving that treewidth is greater than equal to k.
Yes. And I have already proved that treewidth is less than equal to k. Yesterday in the
Yes, that we have
tutorial.
So contradiction of that is like treewidth less than equal to k implies no bramble in this. So contrapositive is I have a bramble of order k.
Yes.
Treewidth is greater than equal to k.
Bramble of order greater than k, then your treewidth is greater than equal to k. This is a contrapositive that we have proved yet. Now, there is another interesting thing that I would like to say, which kind of binds these two things. these two first components of our of our course, and this is a corollary of this result. There is a corollary which says that let H be a graph and let G is
I will write in white chalk.
Sure. Let H be a graph then the class of graphs that excludes or does not contain H as a minor have bounded treewidth if and only if H is planar. So we say that H is my graph that I want to exclude. Then the class of graphs that does not contain H as a minor have bounded treewidth if and only if H is a planar. So this shows a very close relationship between bounded treewidth and planarity. And yeah. The proof is very simple. Let's say, to begin with, let's say H is not planar, then G contains this fancy G contains all planar graphs. And I know that planar graphs have unbounded treewidth. So first direction is okay. That if H is not planar, then the class of graphs that you obtain by excluding H as a minor have unbounded treewidth. Because if H is not planar, then G such that a graph G such that G does not contain H as a minor. That this is my graph class. G is the class of graphs such that G does not contain H as a minor. Then of course class of all planar graphs is a subset of G, and we prove that class of all grids is a subset of planar graphs and they have unbounded treewidth, because as you increase k, your treewidth increases. And this says that if your H is not planar, then the class G has unbounded treewidth. On the other hand,
I think for this you have to say that you have to observe that taking a minor results in planarity. Right?
okay.
Or you can state that and I do it tomorrow.
Yes, I'll just state that if you, can you please repeat your statement?
So
minor
of a planar graph is a planar graph.
Minor of a planar graph is always a planar graph.
So you will never create a non-planar graph by taking a minor.
Yes.
Of a planar graph.
Yes.
Planar graph. So it means all these planar graphs are in your class.
Minor close. So this part is okay. The second part is that if you say that your H is a planar graph, then excluding H, if you exclude H as a minor, then the treewidth of this graph class is bounded. This is the reverse of the statement, and this will complete our proof. And how this is true? Because you take any planar graph, what you can do is you can subdivide. So if you subdivide each edge of a graph any number of times, the graph you obtain by subdividing contains the previous graph as a minor, because you can again contract the edges back. So what you can do is that you can make super fine subdivisions and then snap this to a grid, invisible grid, and you can do this for any planar graph. So what I mean is, you have a very, very small grid. You have to imagine it. It's difficult for me to draw. But let's say that your edge was passing like this. What you can do is that you can think of this like going like this, this, because you can subdivide. And this is how your edge is going now. And you can snap it to a grid. You can delete all the vertices. And now you exclude a grid as a subgraph. So you cannot have a bigger grid now. And because every bigger grid contains this grid as a minor. So the largest grid you can contain as a minor is this. And since you do not contain a k by k grid as a minor, your treewidth is less than equal to f of k.
Can you please repeat this?
Yes.
Maybe show one small example. Is it possible?
Yes. Can I show this one? It's easy, but it will be helpful for me. Okay. So, U1, U2, U3, U4, U5, U6, U7, U8. So you start from here, U1, you go to U2, they make many vertices here, and then you go to U8, you go to U7, go to U6, U5, U4, This way you can snap it to a grid. You can subdivide the edges long enough for any planar graph and you can snap it. And you can think that these edges are deleted. Because you can do that in the minor, you can delete edges. So any graph that contains the bigger grid as a minor contains this also as a minor. Since my graph cannot contain this as a minor, it cannot contain my bigger grid as a minor, and hence its treewidth is bounded by my f of k. So there exists some case for which you can do this for every planar. For every planar graph, there is a fixed k, and since your h is a fixed graph, there exists a k for which you can exclude a k by k grid. And since you are excluding a k by k grid, treewidth is at most f of k. So there is an inherent relationship between treewidth and planarity. Although we are not talking about we are not talking about any embeddings or anything. We are just looking at graph theoretic notions. But these two notions are so beautifully tied with each other that you are bound to end up. If you start with treewidth, you will end up at planarity and vice versa. There are many beautiful relationships between these two.
So if the pivot graph had a vertex with degree greater than 4,
yes,
how are you going to snap it into that?
Yes, because you can again subdivide the edges.
But still you will have a vertex of degree greater than 4.
Yes, contraction. You contract.
H is a minor.
So one of the edges you just.
Okay.
But why we need this? Because if H has only k vertices, we can say that a k by k grid is not there, right?
No, but you have to see H as a minor of.
Your graph has to exclude this as a minor. If it's a, for example, if it's a known K5, if you exclude K5 as a minor, you obtain all grids, for example, and you cannot afford that.
So
Grids are very expensive.
You are taking H, you are modifying it and looking at it as a subgraph of or a minor of K cross K.
A sub, yes.
Actually, you are doing subgraph, but then here's this question about this 5.
Okay, so what you proved is that it is not a minor, like that does not have a K cross K grid as a minor, right? And from that you prove that when we...
If your graph does not have a K by K grid as a minor, your tree width cannot be more than f of K. So your tree width is bounded by some function of K. And your K is a function of H. And since H is a fixed graph, this K is fixed and hence your tree width is bounded.
So the counterpositivity does not contain K cross K, then tree width less than Fk.
Yes.
Yes, there.
Yes.
Okay. So, right. So let's play pops and rollers.
Should we take a small break then?
Yeah.
We're changing the topic?
Yes. divided by we'll talk about Course and Rovers, and a specific version of the Course and Rovers where there are k Course and one visible rover. Now the Course,
What is H for?
H is helicopter. Course and Rovers. So now the game begins in the following manner. The Course either are placed on some vertices of the graph or they are on a helicopter H. So if they want to move from a vertex to another vertex, let's say from U to V, the Course will go to helicopter and then get down at V. So what is happening? Let's say that C1 is the set of vertices occupied by the Course in first round. In the second round, let's say they want to move to k new vertices. So let's say V1, V2.
Helicopter is a vertex?
Sorry?
No, helicopter is not a vertex.
No, helicopter is not a vertex.
Helicopter is not a vertex. It's outside the graph. They fly. Now, so what is happening? Your Course are on some vertices of the graph. They don't move inside the graph. They move above the helicopter. They move over the helicopter. So they are at some set of vertices. So forget about this part. So they are, let's say, a set of vertices. Let's say S1. They are k Course, and next, so they can get most k vertices here. And next, they want to move to, let's say, S2. So
one question, please. From U to helicopter to V, it can be treated as one move?
Yes, I'll explain. So let's say they are at S1, and they want, right now the Course are at positions S1. Some Course is at V1, V2, and let's say Vk. And they want to move to new positions U1 through UK. So what will happen is that there will be some intersection between S1 and S2. Let's say there is some intersection. If this is empty, then also it's the same thing, it doesn't matter. So the people who are occupying S1 intersection S2, they will stay on their own vertices. And now all other Course, they will get on the helicopter to move to their new vertices, S2 vertices. So right now these people will stay, and rest of the Course, which are from S1 minus S2, will get into the helicopter and they will get down at S2 minus S1.
That means all Course have the same power and same scale.
Same power, same scale. So this is what the Course will do. Now, here are your Course. While your Course are on the ground, the moment some Course go up, now before they come down, they go up and they come down. This is one round. So while they are up, the rover is free to move. Rover knows where they are coming down. It is declared. So when the helicopter goes above a vertex, rover sees which are the vertices the Course are getting down to, and now the rover has the access to move. Now the rover can move. And rover is very fast. Think of the rover having a very fast speed bike. And rover now can move, but of course it cannot move through a vertex that is occupied by a Course. But it can move to any other vertex in the graph. It can move throughout the graph. It is very fast.
It may not adjacent.
Not to an adjacent vertex, to any vertex. It has infinite speed. It cannot just cross, think of it as having speed n, the number of vertices in the graph, or infinite speed. It just cannot cross. Also, the rover is always visible to the Course. Course know the exact position of the rover. And this is a game. Is the game clear?
Maybe can you give one example?
What's the goal of the game?
Yes.
I have one question. So, is there any work which have done like that you talk about rover has an arbitrary speed, Course also has an arbitrary speed. This work is done?
Yes. I'll talk about it later after the talk.
So some Course are alternately they appear, disappear.
No. Yeah, on the graph they appear and disappear, but to the rover they are always visible. So in one move, a cope takes a very large jump, and before it is about to land, the rover can escape. And the goal of the cope in the end is to land a cope on the same vertex as rover. So if my rover is occupied here, what I want is that my cope goes on a helicopter and lands on this vertex. And this is only possible if it cannot move, otherwise it will run away. So before this happens, you have to lock.
So when the cops are landing,
Yes.
at that time the robbers are not there, right? Otherwise I can always land on the
When the rover cope is about to land, rover is free to move.
So what I'm saying is, so that
rover
means
sees the
cop
copes
is
and
making
can
a
move.
decision. Cop is making a decision and
Yes.
you cannot change it. While the robber is moving.
No.
Okay.
Cope has committed. When the cope is coming down,
That was my question.
in fact, think of it like this if you want. If you don't want to think discretely, think that rover is free to move at any point. Whenever the rover chooses, it can move. Rover is seeing the time in an analog, continuous fashion instead of discrete. But that is a bit difficult to see. So that's why I think. So it jumps, and before it is about to come, my rover can move.
And all cops go to same vertex or
No. Every cope targets a vertex and goes to that vertex. Every cope can choose the own vertex. Sorry.
Helicopter can carry any number of cops.
Let's say you have K helicopters. Everybody is rich. They have their own helicopter.
Can two cope land on the same vertex?
Yes. Two caps can land on the same vertex. Multiple copes can occupy the same vertex.
So the objective of the game is to sort of corner the robber in such a way that he can't move and
Yes.
a cop should land onto that robber.
Exactly.
But robot can move, but he can jump anywhere.
So let's say Shomenda.
It cannot cross a robber.
Shomenda.
If you show one example, maybe a path or something.
Okay, you see minimize the number of cops, right?
Oh, if the robot is in the printer, then it cannot move.
C1 is here and C2 is here. Let's say. Or if you wish, C1 and C2 are here. You are rover, you go here. I pick my cope and I declare that I am coming here. The rover cannot run away.
Why?
Because it has to go to the center.
It cannot run.
Cross through a cop.
The rover moves in the graph.
So that means robot can move anywhere, but to some vertices.
Through the vertices, but cannot run through a cope. It can take any path. It has infinite speed. It can take any path that does not contain any cope.
Any cops, that is the.
There should not be any cope.
So when are you saying a vertex is occupied? Like all cops are going into the helicopter,
No.
right?
Some cops.
Those who are changing.
As I explained, S1 is my current position. S2 is my next projected position. So here S1 was, let's say, U. S1 was only U1, both cops are at U. And now my next position was U and let's call it V1. Next position was U and V1. So one cop which was at U will stay at U. So the cops at S1 intersection S2 will stay at their positions. The cops at S1 minus S2 will get into helicopters to move to S2 minus S1. Is this clear now?
So,
only one rover. That is sufficient.
So in a tree, three cops should be sufficient, but are two cops sufficient?
In trees, two cops are sufficient. So let's take an example of a tree.
Because of
Yes.
Then in the next, that replacement is always possible that we
Yeah, it is true.
move from there. And then in the next
So that cop has a whole knowledge of the graph.
Yes.
It has a knowledge of the graph.
Everybody has all the knowledge of the graph. Everybody knows the topology.
I saw similar one. where they didn't take the information.
Yes, yes.
This thing is not there.
So
There are many variants. We are talking about this variant for a reason. And the reason is, I'll say after this example. So, as you said, for this, 3 is obvious, but we can do using 2 cops also. Let's say I have 2 cops, C1 and C2. So there is a tree here and there is a tree here. Without loss of generality, let's say that robber is somewhere here. I pick my one cop and I move that cop here. In that time, it could have moved anywhere here. So let's say it stayed somewhere in this region only. Now I pick my C1 and I place my C1 here. My robber could have moved either here or it could have gone here by the time I was landing. So when I was in the helicopter, my robber was free to move there. But now I can move my C2 and I place my C2 here.
Any of these two.
Yeah, but now they can see the robber.
Robber is always visible.
Yes. No, you did not put the robber. So.
Yes. So let's say robber was somewhere here. Now it's in one of these 2 vertices. I pick and now robber cannot move. I move here.
After finite number of rounds, we can
Capture the robber in a tree using 2 cops. In fact, this is
one cop. One cop is enough.
One cop is not enough even for an edge.
zigzag.
So this is your cop. Robber starts here. You go in the helicopter. You come if you want to come down. My robber goes here.
Zigzag.
And this goes on forever. Okay? Now, first I'll say the result and then I'll say why this is important. The thing is, let's say that cop number of this graph, which is the minimum number of cops required for this game to capture the robber, is exactly equal to treewidth plus 1. So this is a complete characterization. This game characterizes the treewidth of a graph. And so there are in fact multiple ways through which we can prove this result. The easiest way is the following. Let's say you have a tree decomposition. And I'm saying that let's say we have a tree decomposition of width k, then each bag is of size at most k plus 1. And here is a strategy to capture the robber using k plus 1 cops. I place all of my cops in the bag of the root node. I do what I did for trees. I place all of my cops here. As we know, this is a separator. As long as my cops are here, my robber is either restricted to this direction or to this direction. Okay? Now, I know it is restricted to one of the children. Let's say it was restricted here. What I do is, I also know that, let's say this node was T. R intersection T is also a separator. What I do is that I keep intersection BT is a separator. Now what I do, I keep my cops at the intersection. I lift my cops from here and they go here. Since I have k, this decomposition is k and I have k plus 1 cops, they are always able to fill the bag completely. So they will come and they will fill this bag. And now my robber is restricted to one of the children. And I can repeat what I was doing for trees and what I was saying here. So if right now I am at a node T and my children, the subtree rooted at T1, which is my child, contains the robber, I keep my cops at VT intersection VT1 as it is. I move other cops from VT and I place them at VT prime. And this is the easy result.
All the cops the root node will be jumped to this node?
No problem. The people at the intersection will stay because that is a separator. And here we use the separator property that we proved yesterday.
Otherwise, rover can jump to other branch.
Yes.
Not jump. Go.
Go to, sorry. Again.
So the T we have chosen according to that in which subtree the robot.
Yes. And the robot is visible. So we can choose.
The vertices which are not in the intersection are putting in the subtree.
Sorry. Vertices that are not?
In the intersection.
Yes.
We are putting in the subtree.
We are putting, so this was my T, this is my T prime. The vertices that are in intersection stays, everybody else flies in the helicopter, comes here and occupies the rest of the vertices.
No, but also please realize that those two bags are drawn differently and adjacent, but the intersection, they are actually the same set, even though physically they look different. So you can think of the robot there, cops there, and
At
here.
any point of time, the robber cannot jump to another branch of the tree because that is a separator.
Exactly. And you block the road of the separator. So this is one way to prove that these many cops are sufficient, A plus 1 cops are sufficient. Now we will use another thing which are called havens.
How do we know that we don't exhaust the number of cops at the separators there?
Each bag has K plus 1.
Each bag has size at most K plus 1. You have K plus 1 cops. If two people have intersection, so I am K plus, I am at most K plus 1, I intersect with someone. Of course, if these people are occupied, there are K plus 1 minus these many people available, which can fly to come. So let's say I have the total size is less than equal to K plus 1. Let's say this has size L, which is less than K plus 1, less than equal to K plus 1. So if these people are occupied, I have total K plus 1 cops minus L are occupied here, and the total people I need to occupy are less than equal to K plus 1 minus L. Equal. Simple. So it's not difficult to see. So sorry. Okay. Now we define something called a haven. Till now we have looked at the strategy of the cop. What is cop doing? It is moving in one particular fashion. What can be a possible strategy?
Till now you have proved that cop number is less than equal to treewidth plus 1.
Treewidth plus
It's the other way around.
Yeah. Yes, but maybe I'll do the same thing using a different technique. So, haven, I'll define something called haven. I want to give some ways to look at the tree width and tree decomposition and brambles and why they are important and why they came into existence. And for this, I will define something called haven, which is a way to get strategies for the rover. So what is essentially the rover is doing? Rover is at some component. The cops fly up, some cops fly up. The rover goes to some other part in the graph and it wants to keep doing this forever. At what point can we say that it can keep doing this? And I'll try to give that particular thing and I will define haven. So, and similar to havens are very closely related to brambles, and here also we'll use similar terms. So I'll say that haven of order, we call that our brambles also have order. So havens of order K. What are our havens of order K? It is a mapping beta for every subset of my graph X of size X is a subset of BG and size of X is less than equal to yeah, less than k. So for every subset of x that is of size at most k, I define a mapping from x to, where do I define? To some connected component c of g, connected component c of g minus x. So g minus x may have some connected components. I will give a mapping beta from x to one of these connected components. And what is the additional property? That for every, from x also I have a mapping. Similarly, for y also I have a mapping to connected components of g minus y, to some connected component of g minus y. So beta goes from x to this g minus x, and y, beta for y also goes to g minus y. And the requirement is,
but the entire image is inside one connected component.
Sorry?
The entire image of x is in one connected component.
It's not an image actually, I made a mistake. Beta of x is equal to, so it goes to, I define beta of x as, beta is a function that takes as input x.
Okay.
Its mapping is all like, it goes from,
let's say cx, let's say capital Cx.
All subsets of v of g, the domain is this, the domain is this. All subsets of Vg of size less than k.
But you were saying something like component?
Yes, and this is the domain.
This is the domain. This is the domain.
Yes, and the range is, it's difficult to write in this term. For each component, for each of this part, for each element x, my range should come from g, a connected components of g minus x. Delete x from g.
This is
so you can
yes.
Component or subgraph?
Connected component, complete connected component.
So you can write beta x is a connected component of g minus x.
Yes, beta x is a connected component of g minus x. Okay.
For all x.
For all x, you need to do this.
G less than equal to k. This is your beta.
Yes. Now you have to have an additional property to call it a heaven, that beta x and beta y should touch. So for every connected component, for every subset of Bg of size at most k, less than k, you should define a connected component of G minus this set, and all these sets must touch. Sorry?
For all possibility of x.
For all possible x. For all subsets of size less than or equal to k. And this is very close to Brambles in the sense that you have a haven of order k if and only if you have a Bramble of order k, which I will show now. How to go between each other. Is the definition clear? Like, let's say, so you have this g, this is your x. So this is your x, and these are your components of g minus x. Beta maps x to one of these components. Is it clear? You have x, these are connected components of g minus x, and beta should do this, and our mapping does it for every x of size at most k, and for every two distinct x and y, they should touch, either they should overlap or they should have an edge in the same manner as they had. And we say that the proof that we want to say,
Why you define this actually? Is there any intuition?
sorry?
Is there any intuition to define this type of thing?
Yes. So,
to capture the robbers.
Yes, this is the strategy of the robber, because what the robber will do, let's say you have less than k copes, and you want to show that you have a k heaven. You have a k heaven. So for every possible placement of less than k copes, there is a connected component where you are lying, where you are living, where you are free. Now, these k copes will declare a new possible position. But when they will declare a new possible position, observe that that new possible position also have a mapping. And by definition, these two mappings touch. These two new heavens, they touch each other. And by the time you go here, you can go to this new heaven and you are safe forever with less than k copes. This is used to give a lower bound on the number of copes required. If you can show that you have a heaven of order k, then you are safe. And you can show, what I will show now is that you have a heaven of order k if and only if you have a Bramble of order k. And it's very, first of all, to see that you have a Bramble of order k. Just give me a moment.
So if we have this heaven of order k and we have less than k cop, then is it saying that we have a strategy where rover always wins?
Yes. So you let's say you have less than k copes, but you have a heaven of order k. You occupy these copes, and to you are mapped a connected component of G minus this set. You are living here. Now your copes will declare, let's say your copes were at x, now your copes declare that they want to move to y. They can have some vertices like this, but for this also, they have a heaven. When they are in the air, they are at a subset of these vertices, and this heaven and its heaven is somewhere like this. It doesn't touch it, maybe it touches this, but they are connected. This is not occupied by a cop, this is not occupied by a cop, so the cop can move here, the rover can move here. And for every possible movement of the cop, there is a good movement of the rover, and the rover can keep repeating it forever to show that it has a winning strategy. And now, let's say that you have a Bramble of order k in your graph. By definition, it is a heaven. Let's see. Okay. Now, what is my Bramble? To refresh from moment, we have some components, some connected subgraphs, C1 to Ck, and I have Bramble of order k. It means if I take any subset of my vertices of my graph of order k minus 1, it will miss at least one of them. Okay? So if I take any k vertices x, it will miss at least one of them. It will not hit one of them. I map x here. And it is very easy to see that this is a heaven. For every subset of less than k vertices, I miss at least one of them. And since they touch each other, by definition, it's a heaven also. And similarly, if you have a heaven, of course, no k vertices can hit this because by definition.
Every Bramble is a haven and vice versa, or every Bramble is a haven but not vice versa?
No, both. Yes. If you have a Bramble of order k, this heating set size is k, yes. At least k. Heating set size of this Bramble, this has order k, it means that heating set of this is greater than or equal to k. So if you take any set x of size less than or equal to less than k, if you take any set of size strictly less than k, it will miss at least one of these components.
So that K and this K is not related, right? C1, C2, Ck.
Same.
No.
That K
Ah,
is-
sorry. Yes, you are right. This is L.
This is right.
Yes.
And the size
It
of
was a
the bramble
mistake.
is the size of the minimum heating set, right?
Yes.
So it is exactly equal to K then.
Greater than equal to K, yes. This is greater than equal to K. Heating set is greater than equal to K. So if you take any set X of vertices X, for this set, you will miss at least one of these components. You will miss at least one of these components. So you make beta of X is that thing, C1. Beta of X is equal to C1. And for every such subset of size less than K, you will miss at least one of them. These are connected by definition, and they touch each other by definition. They will form a heaven. And similarly, if you have a heaven, you have, so let's say, you have some components for every subset. You have some components for every subset of size strictly less than K. You have a component. All of these components, they touch each other. So you get the first definition. And the second thing that you need is that no less than K vertices should be able to touch all of them. By definition, if you have less than K vertices, this lies outside. One of them lies outside. This was the definition. If you have less than K vertices here, you took any less than K vertices here, one of them is not hit by this set. In the heaven also, because it's outside. So these two are the same things. So if you can say that you have a heaven of order K, you can say that you have a Bramble of order K. And I'll finish in 5 minutes by saying 1-2 more things. I'll just give an intuition of the other side of the proof. Unfortunately, I'll not be able to complete it.
You can put it in tutorial.
Yes. So, this also proves that. So, if you have heaven of order A, then Cope number of G is greater than K. And so, Bramble is equal to heaven, which is greater than K, then your Cope number is greater than K, strictly greater than K. And now, what does it say? I'll think about this in 2 minutes. I'll speak something else. So now also let's think about, we just thought about the strategy of the rover. What does rover do? Rover tries to find havens in the graph. What does Cope do? How does a Cope strategy works? So essentially, a Cope strategy is so there is something called a search tree. How does this work? How does search trees work? So Cope say that we begin at a particular position, which is the root of my tree. We say that we start with this position. Next, rover does something, and depending on what rover does, Copes do something else. If rover does this, rover moves in a particular fashion, next move is this, next move is this, and this way I make a tree of what my actions are going to be, depending on the possible moves of the rover. So this is called a search tree. Now, what are these are my nodes of my search tree, and each node corresponds to some vertices. Now, let's say I impose a new restriction. I say that not only I need to search the rover, I need to search the rover in a monotone manner. And what is monotone manner? That if my Cope comes to a vertex V, if it leaves vertex V, it should not visit V again. So it should capture the rover monotonically. It should move monotonically. Let's say I impose this condition as well of search. And the later proof comes into proving that monotone Cope number, like monotonicity is not expensive. Monotone Cope number is equal to normal Cope number. But what I show now is that monotone Cope number essentially gives us a tree decomposition. This search tree is a tree decomposition. This is what I do.
So using treewidth, what we did is monotonically earlier.
It was I can't say immediately. If a vertex is connected, you stay connected. Maybe it's monotonic, yes. I'm not sure, sorry. I need to think more.
And he was in the intersection and come down, it's in the intersection and it is to the entire path.
Yes. So, but yeah, you stay at the intersection, you go to a new vertex, you never go back to a vertex. Yes, it was monotonic. Yeah. So what we will show now is that yeah. So it was a yes, we are right. It was a monotone strategy, and in fact, we'll show that monotone strategy is exactly same as the treewidth. We have already seen that monotone Cope number is less than or equal to treewidth plus 1, and what I will show now here is that my treewidth is this monotonic Cope number is greater than or equal to treewidth plus 1. This is what I will show now. Okay. So remember that I imposed one particular restriction, that my search strategy needs to be monotone. If I leave a vertex, I should not go to that vertex again ever. Here, what I was doing now, what should be some properties of my search strategy? First property is that can we ever clear a graph without shooting at a vertex? Can I miss a vertex of my graph V and clear my graph? My rover could have stayed on that vertex for all of the existence. So when I'm making this whole my search diagram, every vertex should be short at some point of time. So my first condition is that each vertex V in VG, for all V in VG, V should be contained in some bag of T, where T is a norm. This is my essential condition of my strategy. Next, let's say I have an edge, U and V. If at some point of time, if at no point in time, I shoot at both of these vertices simultaneously, can I clean this edge? Because if I only shoot in one round here, my rover could be here. My rover can always stay on this edge. When I'm shooting at this part, the rover is at U, and when I'm shooting at U, my rover is at V. It can oscillate between this edge forever. So it must happen is that in some shot here, I must shoot at every edge. For all edge E in E of G, both vertices of E should be contained in B of T for some V. So, if you remember, these two are our condition of being a tree decomposition, like of this thing being a tree decomposition. Our third condition is that if a vertex V appears somewhere, the subtree induced by the bags it appeared in should be connected. This is our third condition. And this is taken care by monotonicity. Why is it taken care by monotonicity? Let's say that I shot at a vertex here, and somewhere here I shoot at it again. Then I must have shot in all of these bags also continuously. And since I'm making this search tree beforehand, so if I shoot at a vertex here, I should shoot at all of these, and if I shoot somewhere here, I shoot at all of these, and this intuitively is not very difficult to see. that the subtree imposed by the bags containing a vertex is connected. So this is our third condition of my tree decomposition, connectedness. And this is only possible because of monotonicity. That if I am hitting at a vertex, I should be, if I am present on a vertex, I am present on a vertex, I should be present in all these rounds. So this vertex should be contained everywhere. Since in each round I am shooting, let's say I am shooting at most k plus 1 people, the width of this decomposition becomes A. So treewidth of my graph G is less than equal to monotonic curve number minus 1, and we get this. And the rest of the proof, whatever remains, is proving that monotonicity is not expensive. Monotonic curve number is equal to curve number, and curve number is equal to Brambles, and hence all of these notions, they collide, and this theorem is also proved. Is this last part clear? If there is any doubts, you can ask now. I was big. Yes. Agree. Yes. Okay. Now, what I want now is that if I am shooting at a particular vertex, I should if I am present at a particular vertex, I should be present at it continuously, and then I move out. If I move out, I cannot come back. Okay? So, if in this particular branch, let's say I shoot at a vertex B. Okay? I shoot it here and I shoot it here. Then by definition I need to shoot here as well. I need to be present at this vertex.
So you are proving that monotonicity like connectedness or the
Monotonicity requires connectedness. This monotonicity here, if this strategy needs to be monotone, I am saying this gives us a tree decomposition. Whatever my shootings were, they will give me a tree decomposition. And these three properties are coming because if this has to be a successful strategy, these two conditions should be there. That every vertex should be short and every edge should be in some bag. The third condition, connectedness, comes from monotonicity. If I require this search strategy to be monotone, then if I am shooting at a vertex, I should shoot connected in a connected fashion.
Connectivity is lost, then how monotonicity is lost there? So that's the question.
Oh, I did not say that. I said that since my strategy needs to be monotone, this subtree is connected. This monotonicity implies the connectedness property, and hence this is a tree decomposition. Also, what is this? Okay, let me say this also. What does this tree signify? This tree signifies that what is the strategy? I do something, Robert does something, I go in one direction. I go in that direction. If Robert does something, I go here. Robert does something else. By the time I reach the root, the Robert is captured. So each root to leaf path should contain all vertices. Hence, for everything, like if you shoot U here, you shoot U here, there is a common ancestor where U is short, and by monotonicity, it's just a matter of some inequalities. And this should be it if there are no questions.
So this Brambles and Heaven, especially Brambles, this is also a strategy to prove lower bound, right?
Yes.
This can be used to prove lower bound.
These are proved only for more than the only use I know is to give lower bounds on treewidth. subset of size at most of size less than k, for every subset of size less than k, you have a fixed place where you can go. Brembus don't give you any such thing. Heaven is a slightly more complicated tool, which has exactly the same power, but it gives you this text. How you can go from one context to another. This Scope number relates treewidth to heavens, and heavens are related to Brembus, and Brembus again go back to treewidth, and then you get everything. There are just some missing, there are some very little details missing, and it is done. Any more questions? Now I'll be happy to discuss
for the student presentation, so total I think 36 people has registered, so but 33 came. So there will be 33 presentations total, and some people are coming next week, so they will definitely do it next week. But what I'm asking is today we are running pretty late, so either we do 5 today and or we don't do today. She's hinting something like that. So as you wish. But what we wanted initially is to keep the Friday free, because if you plan a trip somewhere, weekend trip, you know, Friday, Saturday, Sunday. So
not free. It's not free. Friday is not free. I mean,
no, but evening.
not too late.
Yeah. I mean, around this time they can go. After 4 o'clock. That's. Usually the trains to Humphrey or something is around 6, so it will give you enough time if you guys can make groups and plan something. So what do you want? So
if we start from tomorrow, then having 6 presentation every day, then we will do 6 days.
No, let's not make it 6 days. If you can be done by next week Tuesday, it's good, because some people have to prepare for exams. So if you see the schedule, Wednesday and Thursday we finish early, and because to leave time for preparation for exam on Friday. So that we can do. So, but tomorrow we can finish a bit quickly, and let's see. Let's try. So Shoro, you should be there at 8:20 tomorrow for the streaming. Okay. And others also try. I know it's really difficult. I know. Streaming whenever the streaming is required, corresponding. Thank you. तो वही कॉल करेगा, ठीक है? आपका नंबर भी दे दीजिए. Thank you. Thank you so much. Yeah, so tomorrow I think first half is 2 p.m. I can recover it. Finish now? Okay. No, I have to ask you. You are the boss.
I mean, as you said, if we finish now, that means on Friday we will not finish. That means Friday we will not finish.
No, we will do it on Monday and Tuesday next week. So Wednesday, Thursday, and Monday, Tuesday. Done. Okay.
Thanks. See you tomorrow.